The red dust of Mars swirls up as a robotic arm works layer by layer, builds a habitat out of nothing but local materials regulated without a single building block having to come from Earth. This is no longer a distant vision. This is the reality of 3D printing technology, which holds the key to settling the Moon and Mars. Today we are diving deep into this key technology. How does it actually work? Which projects and companies are pushing it forward? And where is it already being used? From rocket engines to biological organs to entire buildings. We also look at how 3D printing is making our lives here on Earth much easier, from medicine to automotive, and why this is the game changer for a multi-planetary future. My name is Serwan, and this is Mars Chronicles. Let's take off. Let's start right away with the basics. 3D printing, or additive manufacturing, is a process where objects are built up layer by layer based on digital models. For example, it begins with a computer-aided design sliced into layers just micrometers thick. There are three main categories of 3D printers. The first are printers that use filament in the fused deposition modeling process. In English, that's called fused deposition modeling or fused deposition modeling. The second type are resin printers, which use a technique called stereolithography, or stereolithography for short, to solidify liquid resin. The third type are those that use selective laser sintering to process powder into structures. The abbreviation for this is SLS, but it has nothing to do with the unpopular Artemis rocket. With fused deposition modeling, it melts plastic or metal and extrudes it. With stereolithography, ultraviolet light cures liquid resin. And with SLS, a laser sinters powder into solid shapes. The advantage? No waste, complex geometries without molds, and customization directly on site, perfect for space. Fly with less mass, use local resources, regolith on the Moon or Mars, mixed with binders into concrete-like material. Currently, as of December 2025, printers like the one from Icon reach speeds of 0.5 meters per hour for walls, with resolutions under 0.1 mm for precision parts. The story in space travel began in 2014 with the first 3D printer on the International Space Station made in space's EMF. The spare parts printer printed a wrench that was sent up by email. National Aeronautics and Space Administration then pushed the 3D printed habitat challenge between 2015 and 2019. The winner of this challenge was AI Space Factory with Marcia, a cylindrical habitat made of basalt fiber reinforced biopolymer composite, which is built autonomously. Today, in 2015, Redwire's Archinaut is on the International Space Station under pressure structures in a vacuum. European Space Agency is testing lunar 3D printing with regolith simulant in Cologne. And China's China National Space Administration is planning a printer for moon rocks for Chang'e 8 in 2028. The boom from a market volume of 4 billion in 2015 to over 20 billion in 2025 is driven, among other things, by SpaceX's printed Raptor parts, but also fueled by companies like Relativity Space and several others. And now back to 3D printing. Let's take a closer look at where this fascinating 3D printing technology is actually being used in space travel. And believe me, this is an area that should excite all of us. Habitats, meaning the living and working spaces for astronauts, are absolutely the star here because they form the foundation for long-term settlement. Let's take, for example, ICON's Project Olympus, a groundbreaking initiative in cooperation with National Aeronautics and Space Administration since 2020. They print habitats for the Moon directly from regolith, which is the loose lunar soil, and in 2025, they have an impressive 158 square meter simulator model in Texas called Mars Dune Alpha, where crews can simulate Mars conditions for an entire year to test real-life challenges. Their Vulcan printer, a huge robotic system, uses lavacrete, a special concrete based on basalt, which is abundantly available on Mars. It builds layer by layer with a thickness of only 1 centimeter per layer, constructing structures in just a few hours, which greatly shortens construction time and saves resources. So, when I say that robots will pre-produce habitats on Mars before the first humans arrive, many people probably imagine humanoid robots. But such 3D printers are ultimately also robots, and they will play a key role. Another highlight is the Marsha project by AI Space Factory. In the 2025 update, they are testing in the desert with autonomous robots that transform regolith into stable forms through sintering, meaning heating and compacting, to create habitats that are not only robust but also energy efficient. And the European Space Agency is fully involved. They are pursuing different approaches and technologies with several projects. For example, with the Spaceship European Rover Challenge initiative, they have printed building blocks made from simulated lunar regolith. It looks similarly promising for tools and smaller parts. On the International Space Station, they've been printing simple things like wrenches directly on site since 2014. And in 2025, Redwire's Fab Lab further developed the technology to even produce metal parts, which revolutionizes repairs in space and minimizes dependence on final deliveries. I've already printed a few tools here at home with my Core 1. I printed this super sturdy scraper in about half an hour. And even though my printer is an affordable device, it prints with an ease and precision that meets all industrial standards. A few years ago, none of this was imaginable. The same kind of innovation is happening with vehicles. National Aeronautics and Space Administration's Viper rover, which is scheduled to land on the moon in 2017, has 3D printed wheels that are specially optimized for the uneven terrain. And Astrobotic's Peregrine lander integrates parts made from titanium printing, which are lighter and stronger than traditionally manufactured components. This makes the mission safer and more efficient, apart from the fact that the Peregrine lander didn't manage to land on the moon. And in my eyes, the supreme discipline, both in space travel in general and in 3D printing engine manufacturing. Relativity Space's original idea was to produce their entire rocket using 3D printers. However, they have moved away from this original idea a bit. They still rely heavily on this technology, but not for everything anymore. Here on Earth, we have perfected manufacturing techniques for industrial parts. So for many components, it makes little to no sense to 3D print them on Earth. On the Moon, Mars, and in orbit, it's a completely different story. In any case, they manufacture their engines using selective laser sintering. This enables the production of structures that traditional techniques do not allow. Just think about the cooling channels in the walls of engines. In the legendary F1 engine of the Saturn V, such channels were painstakingly created by hand by welding thin tubes onto the engine. Today, these are integrated directly into the engine walls. SpaceX also increasingly relies on 3D printing for the production of their Raptor engine, especially the Raptor 3. It may not be the fastest manufacturing technique, but it is highly efficient and requires relatively few man-hours. If you want to produce more, you simply have to set up more machines that work in parallel. I have to emphasize this again. Here on Earth, 3D printing is not a cure-all because we already have many highly specialized manufacturing companies that are excellently equipped. We won't be hauling all kinds of industrial facilities into orbit and to Mars. Most applications will manufacture everything using 3D printing. So a very large part of every cargo delivery will be 3D printers and accessories for them, similar to the von Neumann probe. We deliver replacement parts until there are enough of them that they can replicate themselves. For engines, 3D printing is a real game changer. It enables complex designs that would be impossible with traditional methods. Relativity Space prints their Terran rocket almost entirely in 3D. The EON engine chamber, made from a copper alloy, is printed in one piece, reducing parts from hundreds to a single one and saving 60 days of production time. In 2025, they announced with Terran R that they will print 95% of the rocket. First launch in 2026. By the way, SpaceX doesn't just use it for Raptor. Super Draco components are also printed. and in 2025, they tested printed nozzles for better cooling channels. Blue Origin's BE4 has printed turbopumps, and Rocket Lab's Rutherford is the first fully printed engine. Electron beam melting for titanium parts. The advantage: lighter, more efficient, cheaper. The cost per engine drops by 50% in one go. For buildings and habitats, it's about in-situ resource utilization, or in-situ resource utilization for short, which means using local materials. ICON, one of the participants in the National Aeronautics and Space Administration 3D Printed Habitat Challenge, using the Vulcan printer, they will simulate Mars habitats at the Johnson Space Center in 2025, printing 3-meter-high regolith walls in hours. Their Olympus project targets lunar bases, with robots autonomously printing using binders like polymer or sulfur. The European Space Agency is advancing its Moon Village concept, and this year, in 2025, they conducted intensive tests in Nordvik on 3D printing with regolith using laser sintering to create stable habitats. These can reach up to 10 meters in diameter and are perfectly adapted to lunar conditions. At the same time, Redwire is making progress with their Archinaut project. In 2025, it will print beams and structures directly in the vacuum on the International Space Station, enabling component construction in orbit and reducing costly transports from Earth. And then there's the Lunar Habitat from Hassel, which in its latest update from this year shows a close cooperation with European Space Agency, where inflatable cores are combined with a 3D printed shell made from moon dust to create lightweight but robust shelters that can be quickly built and expanded. Since 2014, the International Space Station has 3D printed over 200 spare parts and tools. And in 2025, this will even expand to medical tools like syringes, which can be produced on site to remain independent in emergencies. The future looks similarly promising for Mars because robots like Optimus from Tesla, in collaboration with 3D printers, will be able to print parts directly in the future. While National Aeronautics and Space Administration's Fab Lab is planning a multi-material printer for Artemis 2027 that can process both metal and plastic to create versatile components, not just multiple filament colors, but different materials in a single printer. 3D printing technology is also impressively demonstrated in vehicles, and there are already exciting examples that prove their advantages. Take, for example, the Cube rover from Astrobotic, a compact exploration robot for the moon that has a fully 3D printed chassis, which is an impressive 30% lighter than conventional versions, and therefore not only drives more energy efficiently, but also extends battery life, which is crucial on rough terrain like lunar dust. This year as well, Honeybee Robotics is already testing printed solar sails for the propulsion systems. The lightweight and flexible sails generate thrust through sunlight to gently propel vehicles forward, all without consuming any fuel. This revolutionizes the range on long missions and minimizes the dependence on heavy tanks. On Earth, 3D printing is already simplifying our lives enormously, and the applications are so diverse that they are noticeable in almost every field. In medicine, personalized prosthetics like the Hero arm from Open Bionics, developed for children in 2025, can now be 3D printed in just a few hours, at cost under 1,000 euros, which is not only affordable, but also allows for a perfect fit and greatly improves the quality of life for those affected. When it comes to organs, it goes even further. The Wake Forest Institute for Regenerative Medicine is 3D printing kidney tissue, and clinical trials are planned for 2026. This raises hopes for future transplants that won't require donors and will reduce complications. Yes, you heard that right. Biological tissue from a 3D printer. There are currently several bioprinters on the International Space Station that are fed with living cells, proteins, and nutrients and produce biological tissue. At the moment, it's only enough for bandages made from your own biological tissue. In the future, this technology will print whole organs and body parts. Write in the comments which of your body parts you would like to replace or renew. In the automotive sector, Bugatti uses printed brake calipers made of titanium, which are 40% lighter and thus improve the performance and safety of high-performance vehicles. Meanwhile, Ford uses the technology for prototypes to reduce development time from months to days and bring innovations to the road faster. In the construction industry, Icon is making waves with printed houses in Texas. In 2025, they will build an entire neighborhood in Austin, where a 400 square meter house is constructed in just 48 hours. And that's at 30% lower costs than traditional methods. Now just imagine what's possible if this technology is scaled up. That makes housing construction more sustainable and accessible. For environmental protection, the Ocean Cleanup Project prints buoys from recycled plastic, which are robust and durable to efficiently capture marine debris and protect the oceans. In everyday life, IKEA sells printed furniture parts that can be individually customized, and Adidas shoes with printed soles that provide a perfect fit and maximize comfort. The benefits are obvious. This technology is sustainable, reduces waste with precise manufacturing, and supports local production without lengthy supply chains. And the market is growing rapidly. In 2025 alone, it is expected to reach an impressive $28 billion, driven by increasing applications in industry and consumer sectors. And before we get to the conclusion, a quick note about our Planet Pioneers shop, where you guys are snapping up our embroidered Ad Astra products like hotcakes. With the code MCP, you save 20% on your entire purchase. So go ahead and grab yours now. In short, 3D printing is essential for colonizing Mars. It enables self-sufficient production of habitats, tools, and vehicles from local materials, reduces transport costs by 90%, and makes us independent from Earth. Projects like Icon's Olympus show that we could have the first printed bases on the moon by 2028 with robots building autonomously. Challenges include dust clogging in printers and radiation protection in materials, but National Aeronautics and Space Administration tests in 2025 will solve this. With hybrid binders, on Earth it simplifies everything. Cheaper houses to fight the housing crisis, personalized medicine to fight diseases, and more efficient cars to reduce emissions, just to name a few examples. The optimistic outlook: by 2030, we'll be printing the first cities on Mars, habitats for 100 settlers, printed vehicles for exploration, and tools on demand. Not to mention robotic doctors and surgeons who can replace entire limbs for you in no time. Companies like Relativity are scaling this up for rockets, and with AI integration, printers are getting smarter and learning from mistakes. That's changing our lives. Sustainable production, less waste, innovations for everyone, from farmers in Africa printing parts to doctors working on organs. 3D printing is making the dream of the Red Planet tangible. What do you think? Will 3D printing conquer Mars? Write it in the comments. If you enjoyed this journey through 3D printing technology, subscribe to Mars Chronicles and give it a thumbs up. Big thanks to all channel members and Patreon supporters. For early access to our videos, see the video description below for details. My name is Serwan and this was Mars Chronicles. Thanks for tuning in. Pera spera ad astra. Rest in peace.